everyone. It is my pleasure to give a very quick introduction for Professor Eugenio Oñate for his plenary talk, which will take place in a few minutes. As many of you would have known, Professor Eugenio Oñate was a pioneer for printed element and computational mechanics in general, and has been active in the field for, let's say, 50 years. So, Eugenio was a PhD student at Sloan University. He studied with Oleg Sienkiewicz, one of the most well-known pioneers for finite element methods. He then moved back to Spain, Barcelona, and founded CIMNI, the International Center for Numerical Computational Methods, which has been very active for several decades. And Eugenio has been very active in shaping the field of computational mechanics by serving as the president of ICOMAS and also president of IACM, which is the International Association for Computational Mechanics. We wanted Eugenio to be here as part of CM3P for several times, but he had always been very busy, only until recently when he had more time getting away from the directorial work, management work at CIMNI. Now, for the first time, we are able to have Eugenio here with us to give a plenary talk. So without further ado, let's welcome Eugenio for his plenary talk. Thank you.
Thank you, Chanfum. Yes, it is 50 years since I arrived in Swansea, September 75. 50 years. I finished civil engineering in Valencia, and I arrived in Swansea, where I stayed for almost 4 years. I didn't work with Oleg Sienkiewicz at the beginning. I worked with Ernie Hinton. I did well in my MSc, and then Oleg Sienkiewicz, Professor Sienkiewicz, offered me a grant. But yes, fine. Looks that it was yesterday. Where were you 50 years ago? You know, some of you were, well, most of you weren't born. Well, sorry for the personal, and sorry for, more and more things just happened to me. I got everything ready, but I forgot my charger at the hotel. My wife will kill me. Anyway, so I prepared a kind of after the summer lunch presentation. Hopefully it will be entertaining. That's been the main objective. Of course, some equations will appear, but also some examples that I hope that will help you to not to fall asleep completely. This is a work with a group of researchers from different countries. Sergio is a professor at CIMNE, and Juan Marcelo Jiménez, they are both from Argentina. Francisco Zárate is from Mexico. Alessandro Franchi is from Italy. Alejandro Cornejo is from Spain, is a new lecturer. And Reinhard Lerner, some of you might know, is distinguished professor at George Mason, that he visits us in CIMNE every year. Now, I'm going to try to convince you why these class of problems are important. I think this will be easy. And this is kind of I would say, a class on how are we going to model all those types of flows that have different applications. Okay? And we're going to complicate a bit the problem by assuming that these flows are going to interact with the structures. And again, the term of structure is a general trend. This is a conceptual picture of what are we talking about. We have a container that could be flexible, and then we have three classes of, we have a liquid, could be water, could be oil, and we have three classes of particles that we call it very small, small and large. Then we are going to use these terms to be more specific. If we want a method that is able to analyze each of these particles moving in the fluid, and sometimes all of them together. Examples. I don't have to insist on the importance of this topic. These containers could contain grain, they could contain fluids. You can read yourself the classes of problems that are including with this type of flows. Environmental flows, more and more important. Ships in icy water, etc., etc. Airplanes flying in difficult weather conditions, or vehicles driving in difficult conditions. A very important problem, this of wind erosion in the turbine blades. Painting of cars with spray powder. Filling of land in harbors. We use in dredgings. This is very typical in this part of the world. These blocks, 250 tons, disappearing overnight due to the strength of the waves. Dams that disappear, like this dam in Valencia, my hometown, in 1982, that due to overtopping, failure of the spillways, disappear, creating a devastating effect. And then more, I would say, real life problems, like everyday problems, like excavating in tunnels near the water. This is of higher value, excavating the land, soil 6 kilometers to dredge for oil and gas purposes. And this is even more new problem that you might not be aware, but with this gas conduction underneath the sea, there are problems of landslides, undersea landslides that create water particle structure interaction. Fire was mentioned today, so I'm going to present a couple of applications on fire, if I can. But look at the problems that I have left out. I have to tell you that my experience, being a continuum mechanics guy, there is more potential for application of our concept in the field of particle methods than in continuum mechanics method. You see, you only have to read this list and you will agree with me. So now, some definitions, because I don't have time to explain all the details. Physical scale is the Kolmogorov scale. Okay, this is a physical scale, defining the smallest scale in a fluid. Now we have meshes, small and large, coarse and fine. Now, for particles which are bigger than the final, the fine mesh, and we are going to treat it as a non-homogeneous fluid. I mean, we are going to consider the particles individually. For particles that are smaller than the fine grid, including the Kolmogorov scale, we are going to treat them as an homogeneous fluid. This is important. Now, for instance, the combination of the three particles will mean that these microparticles that are going to be very small and homogeneous, we are going to treat it as a fluid with an equivalent viscosity. Whereas these two classes of particles, they are going to be treated individually. Now, just to break the scene, this was the picture of the tsunami in Japan, and this is this is a kind of very simple application, when you have small particles, large particles flowing. Now, if on top of that, you saw that container, you have a free surface, because you could have an internal fluid and particles. But if on top you have a free surface, modeling the free surface brings in another problem. So I am concerned about free surface particle-laden flows and interacting with the structures. And again with the three classes of particles. And here there are two keywords. First, that I'm going to model the interaction of the particles with the discrete element method. And I will only spend 2 minutes on that. And I'm going to model the free surface with a particular class of method which is called particle finite element method. But here you could bring your own technology if you have a technology for that. Now, discrete element method. We have heard this morning some lectures. You will know that it's a method that assumes that the domain contains physical particles, typically spherical, and then they interact through forces in the boundaries. And they satisfy Newton's law, so it's the simplest equation. And you integrate these equations in time explicitly. Why? Because you have millions of contact interactions. You cannot treat it implicitly. So far, nobody has succeeded. And the challenge is in modeling the forces, the relationship between the forces at the interface, this is a contact interface, Very simple, 3 forces, tangential, 2 tangential and a normal, and this define the behavior of each particular problem that you model, and it's not so easy to characterize. Now, I'm only bringing here something that fits to this conference, that if you want to have a consistent model for discrete elements, it has to be non-local. This brings some new concept. It has to be a Coursera type of model. So the forces, they're not in this particle, they don't only depend on the surrounding particles, they also depend on the particles beyond. So this is what is make it non-local. Why do we need this? Well, so we compute the forces with a kind of average of the stresses using a kind of average, and by introducing this non-local concept, we have in top of the local effect these additional effects that bring the particles surrounding particles. We need this because otherwise this problem will not give you the Poisson effect. If you press here, you will not get Poisson effect. With these non-local terms, you can reproduce Poisson effect. You can reproduce exactly an elastic model with even if the collection of particles is regular. This is only curiosity, but I think it's also interesting. So here you have 2 classes of problems. Believe it or not, the non-cohesive particle field is bigger than the cohesive particle field. Cohesive particles means, this is non-cohesive. Cohesive particles means this, and many other problems. So now we know how we're going to model the particles via the discrete element method. Let's see how we are going to model the free surface. The free surface, we are going to this method that combines basically it's a Lagrangian approach with a remeshing. Lagrangian approach with a remeshing. Lagrangian approach for the fluid with a remeshing. Basically, you have a collection of particles modeling the fluid. Then you press the button using the so-called alpha shape method that comes from computational geometry. You recover the boundaries. And here you can have external domains or even single particles characterized by density. These are material points. They have no mass because it has no geometry. Here I can integrate and get the mass of this, but this is only a point. And then another button, I mesh, I use finite elements because this is my background. You could use finite volumes, you can use finite differences, Best method. Then we move the particles by solving the equations of momentum equations, and what I do is I throw the mesh away. You see, we go from particles to the boundary, boundary to the mesh, mesh to the particles, and again particles to the boundary, boundaries to the mesh, mesh to the boundaries. And here you see a yellow and blue. This is a ship, this is a body, and it's characterized by the density of the particles. So the particles define the properties of the underlying continuum. So this is very simple. You need only to regenerate first, identify the boundaries. Now this is done. It's milliseconds because computational geometry has evolved tremendously in the late last years. And generating a mesh, it was very expensive 20 years back when we started, but now again it is very fast. So you see, this is 2004. We got these examples. You see, this is like a magician. This is the trick, and this is the answer. You know, the mesh is generated. You don't need to regenerate the mesh here, but still we do because this is very fast. You see the boundary, how it recover. Another case, 2004, still very effective today, and you see here. And here we have added also a tool that adds more elements near to the body. So now we know what we're going to do. We are going to use the framework of continuum mechanics, solid mechanics, to model the fluid. This is our fluid with the object inside. Initial configuration, current configuration, updated configuration. You will recognize the terms of continuum mechanics for solid mechanics. Not so common in fluids. And of course, because we have been educated in this framework, then we write equations, which are the equations of a generalized continuum, where this is the acceleration, this is divergence of the stresses, the Cauchy stresses, And the only difference is in the constitutive equation, because we know that some paths might go incompressible, because the fluid, you don't forget that here I have two bodies. This might be incompressible, but this could be compressible. Then I have a generalized constitutive equation for the deviatoric and for the pressure. So I work in terms of a mixed formulation. That, of course, if it is incompressible, this will be divergent, the rate of deformation equals 0, otherwise. And this, for fluids, this is a so-called non-memory material for Newtonian fluids. This is the term that comes from the updating of the internal variables, the stresses for the fluid. The same for the temperature. So basically I skip the convective terms that are difficult to manage in terms of computational stability, as you know, and the penalty is that I have to regenerate the mesh every time. So this, anyway, this shows to show that this was a thesis that you could have a unified continua that could be a fluid, it could be a solid. This is an academic, but show. Boundary conditions. I don't have anything to say. Tractions and velocities prescribed at the boundaries. I have virtual work, or Galerkin. For the velocities, the pressures, and the temperature, equal order elements, I need to stabilize. So in the momentum equations, I have the velocity and the pressure, because it's a mixed formulation, and in the pressure equation, I need the stabilization term that comes from your favorite stability method. It's a Laplacian time of term. We use a particular stability approach, which comes from, we call it finite increment calculus, and this is the stability to ensure non-oscillatory solutions, and the temperature is nothing to say, it's the standard equation for the temperature. Okay, this is how we develop it. Now you could take your solid mechanics code and your fluid mechanics codes and iterate, or you could have a single code. This is done in some new thesis when you develop a code for a generalized continuum that could include fluids that could be incompressible, or it could be compressible, it could be non-Newtonian, and solids. Now, questions. I anticipate questions. Mass conservation. This was the thesis of Alessandro Franchi. This is the most dramatic examples, two streams hitting each other, and we check the mass conservation. Because we lose mass, you can lose mass through the pressure equation, through the stabilization, or through the mesh generation. And we can see here, you see this is 2% accumulated, and we don't introduce mass, you see, because we know the mass that we lose, you could pump mass every time, but we don't do that. You check that the mass that we lose is not big, so it's okay. Then you could add the structure, and you can see this is how we work. Some distinct features of the method. We already heard this morning about how to treat contact between solids when you have an interface that here is a fluid, it's not air, it's water. So in this interface, resembles a bit the interface that Professor Rigas was talking this morning, we introduce a contact, the simplest contact law. And this interface can be made, this is the work of Professor Oliver and others, as thin as possible. But however, we are not interested in the quality of the contact, because if you have these tetrapods that you're going to throw in a harbor, and this, you see these are the contact elements, what you're interested more is to really check where are they going to be placed, So it depends on the quantity of interest, The quantity of interest is the position of the tetrapods, not the contact as in metal forming on other applications. So now we know how to model the fluid, we know how to treat these particles, we put them inside the fluid, and first we consider the so-called mesoparticles. These mesoparticles that are, you see, that they are smaller than the mesh. You see, smaller, this is the side of the mesh, the coarse mesh. And here we use the so-called inverse approach. This is very popular in chemistry, in other fields. Basically, we assume around a node, this is a node in the fluid, that there are a number of particles, you see, smaller than the mesh, and these particles occupy a space. This is like a porosity. So the more particles you have, the less fluid you have. And you have this fluid volume fraction that when it goes to 0 means that you all has no fluid left. and we can go up to almost 0. And this is introducing the equations. In the momentum equations, they see the effect of particle to fluids, which is exactly the same force that fluid to particles. And this is the equations for a fluid containing particles. They are very simple, simple modifications. Conceptually, is interesting, but it's simple. And what are these forces? What are these particles to fluid forces? First, the weight of the particles. Second, the contact a la them, the contact forces that I explained before, tangential and normal forces. The Archimedes force, and the drag. And for the drag, we don't speculate, we go to a book and we take drag for spherical particles. It's very well documented, even for spherical particles, So we take the drag from the model, a model. Otherwise, if you have a very strange particle, you can compute the drag by doing experiments. Okay, and this allows us to compute those forces here. And these are, you see, the equations for the fluid with the particles are exactly the same as without particles, accounting for these terms that I have mentioned. So I will not go with this. Now, particles with the same density of a fluid, particles with a bigger density. Well, these particles fall with the fluid, they fall faster. These are tests, these are like streamlines. These are, you can play with these particles. We have compared our methods with every experiment which is available still. We all ask, have you compared your method with experiments? Yes, we have. But you see, now we want this flow to hit the structure. This is the next challenge. Before that, let me tell you that when you have bigger particles, this is the simplest problem. Because these particles, either they are embedded, embedded in the fluid, or they are treated like body fitted. This is body fitted. Body fitted is that they are fitted within the fluid. Inside you'll have the smaller particles, and this is again the same contact interface in red that will give us the forces between the big particles in the fluid. So now we know how to treat these small particles, a la DEM. These particles, rigid or not rigid, they will hit the boundary of themselves, and they are treated with, if they are rigid, we simply compute the forces at the center of gravity, and then we simply move the particles as rigid body. You see, this is an example, This is an example for which I only have pictures, but the pictures are very nice, you see. Pictures showing the qualitative agreement, because I don't have any numbers for this example. And then we have, over the years, because 2004, over these last 21 years, we have applied this to many problems. Langosteira is in La Coruña, not far from here, which was not a completely successful story of the harbor. But we model, these blocks are 4 times 4 times 4, 64 square cubic meters. And here this is what you don't want to see, the mesh. Because the PFM has finite elements, it has a mesh at every time step, but you don't show the meshes. Nobody wants to see meshes. This is an academic example. You have a lorry, even if this is a 20-ton lorry, the lorry will, you shouldn't drive next to so this is not a very, an interesting feature. Qualitatively, the engineering, from the engineering perspective, you can approximate the tangential force, a very crude approximation, because you might speculate that we don't capture boundary layer effect here, but we can compute a kind of Archer law for the wear, and when we exceed a certain threshold, eliminate this, assign this mass to this node, and transport it. So we can erode. You see, we can actually erode a surface. Just here on the top, see if we can. I don't know if you can see it. I don't see anything here, so maybe I will go further. Another case, a slope, unprotected slope with an overtopping stream. Of course, the slope will disappear. What am I doing? These are movies, only movies, okay? Another movie. This was all funded by, after the tsunami in Japan, with our colleagues from Japan. We worked a number of years. And then, we did many cases until the final challenge is, can we break this wall? Yes, but we need to add then another feature to the method, which is how to model multifractures. And we model multifractures by the simplest approach, which is transforming a finite element into a set of discrete elements. You could have many applications, many ways of modeling fracture. But here we're interested in modeling many fractures. And you will see that this is very effective. Basically, we look to the stresses at this edge. When they exceed a certain amount, we eliminate this part of the element. And then when we have another node breaking, we eliminate the element. So this, we have published this in a number of papers. You will see this is very effective. This is the Brazilian test. And this is the fracture that we will have with different meshes. Very crude fracture, yes, but the interesting thing is, look, the forces. So the method, because of this edge approach, and don't ask me why, is very, we say, consistent. The force that we are trying to get from the Brazilian test is the same with the three meshes, and the same in 3D. Look, this is an example of application of the method. Let's see if this is working. Oh, I have to press. Never have to press. I press. To a single fracture. I will not recommend this method for a single fracture. This shows that it works. But for this, you know that there are many other methods more efficient. But here, this is a tunnel front where you are going to have 40 explosives program. And then here you see, for this case, this method is very effective. You see, you can model very nicely how the fractures are created, and then you can design where you place the explosives. So multi-fracture is very adequate for this method. I don't want to talk about explosions. I'll rather talk about something which is also very obvious. In Spain, we have all this, and also in Portugal, all these Roman churches, and you know that they will not sustain an earthquake. If an earthquake comes, all these churches will fall down. Okay, so anyway, but this is just to show you that this method is very effective for multi-fracture situation, when you're not so much interested in a single fracture in an aircraft or in a steel part. But look, now we are going to throw a stream on this beam where I have a notch here. And I'm going to see that the beam, the notch, is going to enlarge until failure. So now I can model fracture under the effect of the stream. This is in 2D. You see? So now, look, together with our colleagues from Japan, we have modeled this test. This is a flume of 140 meters. You see 12 meters depth, where they place at the end a reinforced slab. Reinforced slab. 6 centimeters. I think this is almost like a 2 by 2. I don't remember exactly the dimensions. And you see, now I'm going to press. I think it has noise. You see, this is small noise. I reduce the noise. This is the wave coming. And this is the only example I know where there is a record of a reinforced concrete structure fractured by a big wave. Okay, so we have reproduced this. But this is how it was. First, we play with PFM to check that the height, the wave height, was the correct one. Then, again here, let's see, because here we play a little trick because the interaction was not so tuned. We compute the forces, and then we apply it to break the wall. And this is a short distance model. See if it works. Well, you can. Oh yes. This is the beam without. This is the slab without reinforcement. This is with reinforcement, but I don't have the videos for this. Okay, I lost track of. Oh. You tell me when I have 5 minutes or 10 minutes left. A field of very high interest, not only engineering, but also financially, if you talked about oil and gas. Excavation. This is PFM applied to excavation. This is a way to generate particles in the context of this lecture. We remove this, when we compute the forces on this domain, and then when exceed a certain amount, we remove this is like the wear applied to the boundaries. You see, it recognizes the strength of the underlying material, and we have applied this to projects in excavating machines. I will go a little fast here. Also to this. Anyway, that was a European project. These are companies that we work in Europe in this field. But where we got the biggest funding for a number of years was from a company called first Weatherford and then ExxonMobil, working in the behavior of the drill tip, how this drill will behave when cutting the soil. And then how these particles will be transported to the surface 5 kilometers in a fluid, which is bentonite. It's not water. Okay, so this is when I link with the former part. This is the simple supported beam case of this class of problems. You know, simple supported beam is the simplest case in structures. So this is the simplest case. You have a jet which impacts a cohesive soil. The particles go up, and then you get them back, and then you count. You look at the mass. So this is simple, but not so simple. This is another test to design the fluid that draws the particle. And this is another case. And this is the outcome. If you have water, you see, let's say this is the bentonite. You see, it says here 0.1 and 0.1. You see, the particles go at the same speed as the fluid. However, because it's dense, if the fluid is water, the particles go much slower. You see 0.3 and less than 0.1. The fluid goes at 0.3 and the particles don't follow the fluid. You want this curve. So this is the courtesy, this is the application for our colleagues. Together with Cathy Butler from NIST, we after September 11, we studied the melting and burning of objects in fire, how objects will burn, and there's a number of papers in this field. There were 2 papers this morning in this session, so if you're interested, I could give you a report on that. This is more, I would say, current. Fire is a very big problem, but this is a hot problem because of the melting of the ice in the poles. And of course, you could have large. This is a kind of cartoon. Typically, what you will have is this situation. This is a real vessel moving in icy water. You can model the forces, linking the forces in ice. Ice mechanics is a field in itself. And you see here, we have the buoyancy effect. This is soft ice, this is hard ice, and at the end of the day what you measure is the forces on the hull. And then with that you design the power engines. This is a project this is how it moves. This is a 3-meter slab of ice. No, it's not 20 centimeters, it's a 3-meter ice. And this is what you get. You take the average of the forces, thick, soft. I don't enter into details. There is a paper published on this. Unfortunately, situation like this, a cartoon, but this is not a cartoon anymore. This is in Lituya Bay, the landslide falling into the reservoir. This was a big disaster. Landslide, and then going. This is a bit old already. So I will show you a more recent example that has been published in a number of journals. This is the Bayon Dam in Italy, 1963. This is the dam. This mountain fall and created one of the largest landslides ever in history. This is the mountain side that fall. This is the dam here, and there were 2 waves, one upstream and the second one downstream, overtopping the dam, which didn't fall. The upstream bore created more damage in terms of casualties than the downstream one. So PFM falling, you see, and moving up. This is very well documented in engineering geology. Together with our colleagues from Politecnico de Milano, and this is a geologist. This is a very nice example of. Now, we have to move very fast now towards the left side of my particle size. What happens if we have billions of particles like during COVID? Then we cannot treat every particle individually. So here we are here, and we are going to homogenize the fluid. It's a little bit similar to what I did in this, but anyway, let me tell you what I'm going to do. I'm going to homogenize that, and here I'm going to use the concept of multiscale. We're going to have an RVE. We are going to, this RVE containing particles of a certain diameter, a certain density, and a certain percentage. And we are going to build a database with the RVE, and with that we are going to analyze the large scale. 5 years ago this was a novelty, now it's a common practice in multiscale. So this is what we're going to do. Here in the RVE, we are going to, which is of unit side, we are going to model the particles, because here I can have a Kolmogorov side mesh, very fine mesh. This is what I'm going to do conceptually. This is the RVE. This is the mesh, and then I'm going to send back the information. This is what we're going to do. Here, this RVE, we are going to compute our catalog from this study, and from this catalog, using machine learning, this is the surrogate model. Well, I didn't say artificial intelligence, it's a synthetic model. This is the catalog that you build once. You build it once for every class of particles. You might spend 3 months building this, but then you have it. And then with this, you can analyze your fluid. So this is a physics-informed, data-driven model. We call it pseudo-DNS, because the quality of the RV mesh is DNS, and there are a number of papers being published on this. And we have published, for instance, this is Reinhard Lohner model every individual particle. Yes, it took him, this is 10 million particles going out per second. He did that, and then with the homogenized, because after all this is an homogenized fluid, we have the same kind of result, validated by looking at the particle densities at different distances, etc., etc. A COVID, we also published paper on the COVID. This is with every particle model, and this is with the homogenize. I skip this. Now, applications, many applications. You have not heard of this technique. Basically, this is particles, there is an electric field that really drives the particles to the painting. This is electropainting, and we have actually modeled this. This is a very interesting practical problem. And this is with the DEM modeling every particle, and this is with the homogenize. And we can see that this takes a few seconds, this will take a few hours. Well, there is a paper also published on this, so I will skip it. You see, but this is how, you see how this is burned. So this is a practical problem that, we are trying to really bring this technology into this application. Now, very fast, we have been working in the erosion of the wind turbines. You can see that they are trying to beat records. I don't know how much. Very interesting enough, Peter, now we are working in bladeless turbines. Only by moving the mast, they create they're still not in the market. Bladeless wind turbines, aeroelastic. Anyway, but this is the case. What we did here is we build erosion of blades to raindrops. We input the rain condition, the environmental conditions. We create a surrogate model for the erosion model, and then we can compute the evolution of the erosion in time. I think I will skip it. I will not give you the details of this. If you are interested, how this is modeled, how this is. There is a paper, with all the details are. I'll show you the last picture at the end. You have things like that. In so many months, the erosion expected is 0.33 millimeters per year. A surrogate model to predict the erosion by educating this. But I want to finish with the the current research, what we are doing. We believe this pseudo-DNS method has a big potential to, I don't like to talk about revolution, but to bring a new insight of very complicated problems. You will see what I'm talking about. First, you have a big formation, 10 kilometers. You have fractures. How will you model, how will you design where you put your wells here? Accounting, for instance, that you are going to pump water or inject water. This is a very difficult problem. Currently, they are doing it with data-driven approaches on the basis of current information. What we have done is we have formalized what is an RBE with fractures. This is an RBE with fractures, defined in terms of length, thickness, percentage. Okay, this is what we have done. So we have applied this conceptual framework to define the physics of the underlying continuum, which is a fractured media, to construct a database. And then we apply it to this large formation. This is a project we are doing with PUCI in Rio de Janeiro, Rayan Reuel, funded by ExxonMobil out of the offsets that they have to pay to Brazil for being able to track oil from there. Anyway, so I will not give you the detail. I already explained you what we're doing. Conceptually, we are building the database, inputs, the number of fractures, etc., etc., and the outputs at the end is permeabilities, the permeabilities of the medium. Okay, and I'll show you an example here. This is an example. You have here your continuum. This is 240 meters. You have 4 wells, and we are playing, injecting here and seeing how much we get here, or injecting here and see how much we get there and there. This is what we're doing. This has also been published, and we can see that using a fine scale simulation by modeling each fracture individually, this is not explained here, we can compute that in seconds we get what it takes hours in the so anyway, so again, let me show you this example. Oh, I cannot, I don't see it, I cannot, because I don't see my screen. Here this will pump water here, and this will flow and leave from this side, so we can see the evolution. This is multi-phase simulation. This is oil and water flowing. I don't see my screen, I rather don't touch it. And now this is ongoing research together with Rail and Error. We believe that this multi-scale approach is the right approach to model turbulence. Why? First of all, air. You only need to build your RBE for air once. You can spend 6 months, 3 months. And then you can apply it to do aeroelastic analysis of cars, trains, planes, whatever. The RBE has two features, the internal RBE and the boundary RBE. And we have applied this to real problems, you will see, with efficiency of 2 orders of magnitude versus in terms of the mesh size needed. So you have to take my word for that. This is the first case we are doing, and I don't have the time or I think you don't want to hear all the details about the quality of the results, which is very good. There is a ongoing paper on that. But basically, by using this pseudo-DNS approach, which means by taking an RBE, educating the RBE on the different boundary conditions in the boundary and inside, you can model turbulence around anybody very fast. We are now trying to convince the turbulence community, which is an impossible task. Almost as impossible as the soil mechanics community, but even I think it's harder. Anyway, now we are, we're doing this with Renal, and now we are of course, because this is a very well documented test. If you want to enter into this game, this data is available, and then you include the complexity of the body, and now we hope to come to the Olympics in this field. And the last field, well, of course, this is with Professor Riggers, we try in this field to convince our colleagues in Europe, because the challenge here is to bring the particles later. This links to my lecture. We're not only interested in the aerodynamics, but with the extreme weather conditions, more and more airplanes are going to fly in conditions where there will be rain particles or it will be hail particles, and you know that nobody wants to find itself in this situation. Also with cars, We are playing with the so-called Hammett body, but now we are trying to model a real car. And again, I finish with this, I think. The objective is every day we're finding, this is not so dramatic, you know, but I think the concepts of how to treat particles in this field will apply. And as industry gets more and more sophisticated, I think I anticipate that this is going to be a topic of research in the future. So combining methods is like in civilizations, combining cultures of particles, finite element method, DEM, FEMDEM, and the pseudo-DNS, we can meet the challenges of this conference. Multiphysics, multi-scale. I didn't put multi-arsentity because this will be another layer of complexity. But yes, maybe I'll finish with this. What is this? My colleague Alessandro Franchi from Italy, he thought of this nice example to finish, and this opens the room for application in fields which probably are most important in our culture, you know, food mechanics. Anyway, with that, I thank you very much for your attention. Thank you.
Thank you, Eugenio, for the exciting presentation. Let's take time for a couple of questions. Who would like to go first?
Yeah, the scale of those simulations seem like they could all be somewhat stochastic in nature, are they, or are they always run deterministically?
So far, deterministic.
Okay.
So far, we run stochastic in the sense that we build this database for the RBE, and then we interpolate from the RBE, but so far the properties of the real world, they are taken as stochastic, deterministic. As I said, this will add another layer of complexity.
Thanks for a very nice talk. I have one curiosity. Is there a reason why you choose to use the Cauchy stress for your Lagrangian formulation as opposed to the pure Kirchhoff?
No.
Which is more natural, I would say.
No. No, this is because we use a simple constitutive model. No, there's no reason for that. Okay. We just so you could use any solid mechanics model, any.
Okay.
I didn't talk either about the time integration, which is another topic that we are actually working very actively, because we think we can have larger time steps than the current time integration method. But so there are many aspects that are left behind. What?
I got a question about your fluid simulation. Is that right? You use a finite element mesh or solid mechanics framework to simulate the fluid in your example. So in that case, I guess as when you pass your larger particles through your fluid domain, which is captured by the mesh, you will have the situation where because the particle size remains the same from one place to another place, but the mesh size keeps changing. Do you have a challenge doing the mapping?
We have to map all the time.
All the time.
All the time. And we map typically at the field variables, we map the increments. And with that we conserve. It's like with mesh refinement.
Problem, yes.
Mesh, so it's the same problem.
Yeah, so
yes.
you have a clever measure.
That was a thesis that it was shown by mapping the increments of the internal variables that we had enough accuracy. And, let me tell you that we use finite elements, but for instance, Juan Jimenez, who is one of the authors, he's doing all the examples. He's a finite volume guy, and he uses OpenFOAM. It's funny how these cultures, he doesn't know about Galerkin, for instance. It's amazing how people are getting specialized, and using these codes, they live within that culture. You could use measures methods as well. A smooth particle, the numerical method doesn't add any new conceptual constraint to the method.
There's no fundamental reason why.
You could use SPH. I tried to convince Javier, but I don't want to start anything new,
Yes, next question.
I was actually going to ask, did you ever compare the PFEM with smoothed particle hydrodynamics?
We did in the past for some benchmarks that we did in the past. The smooth particle hydrodynamics is a very fine method. Unless, while you have to control the free surface, because the surface is smooth, you know, and when you have interaction with the structures, here we recover the free surface every time, you know. Sometimes in the smooth particles you don't worry about this. So this is my only, I would say, concern. But now Professor Bonnet now is going back to the fluid formulation for solids. Now, as you might have heard, you might have seen together with Antonio Hill, you know, they think that this conservation theory, which is basically conservation, conservation is a word from fluid mechanics, you know. Conservation has big potential for solid mechanics. He gave a lecture in this week in one of the seminars in Europe. I don't remember when.
Okay, last question.
Thank you for your presentation. Did you try some mass transfer? Did you try some mass transfer between the particles or things like boiling or evaporation things to use your code or things?
No, we thought about it. No, we didn't. You could add any physics. For instance, you could add any. For instance, in reactive flow, you could add reactions. There is a field called active fluids. Active fluids, they bring in electromagnetic effects between the particles. They bring biological reactions. So you could bring physics inside your problem. This is another equation. This is another transport equation. If you know what you're doing, but every new application has its own specialty. So I think this is a general framework. We thought about it, but we didn't. Thank you.
Thank you.
Okay, I'm conscious about the time, but Eugenio will be here for the coffee break and for the afternoon. So feel free to get hold of him if you have more questions.
Otherwise, you can send me. You can find me in less than 2 clicks. So you can send me an email, and if you want to visit us in Barcelona, I cannot promise I'll be there, but I will really. Most probably I'll be there, but I promise my wife not to commit myself to anything new. But I will make sure that you have a contact there to interact.
Thank you again. Thank you, Eugenio.
And thank you to.